Standard LLMs have a problem. They're black boxes that love to jump to conclusions. But what if you could actually watch an AI think? Today we're using Tunix to re-engineer Gemma 3. We aren't just training it to give answers, we're forcing it to show its work, generating a verifiable step-by-step reasoning trace for everything it does. Reasoning models are different from standard LLMs. As shown here, a standard model gives a direct answer. A reasoning model, on the other hand, provides the steps to arrive at the answer, which we enclose in reasoning tags. We leveraged Tunix, Google's JAX-native library, to fine-tune Gemma 3.1b on cloud TPUs. Recent studies suggest that sub-billion parameter models fail to gain significant benefits from reinforcement learning. They simply lack the exploration capacity. Our solution is strong-to-weak distillation. By using DeepSeek V3 as a teacher, we generated a synthetic dataset of verified reasoning traces. Training Gemma on this curated data provides a cleaner learning signal than RL, resulting in higher accuracy and a far more efficient training run on the TPUs. We curated a mobile-first dataset focusing on high-utility edge tasks, smart replies, notification summarization, and lightweight Python logic, avoiding impractical Olympiad-level math. This is the blueprint for our model's thinking process. In the prompt template, we explicitly instruct the model to wrap its logic in XML tags. We then mirror this in the output template, formatting every single training example to enforce that the reasoning trace must appear before the final answer. Our pipeline splits tokenization into two streams. Crucially, we apply a custom mask, setting the user prompt loss to 0, forcing the model to learn the reasoning logic rather than memorizing the question. We tie everything together using Grain's data loader. It defines a linear pipeline using this operations list and finally stacks them into batches for the TPU. Tunix handles the complexity of distributed training. We simply defined a 2x4 mesh for FSDP and tensor parallelism, and the library automatically sharded our model across the TPU version 5e chips. This is the final assembly. We define the optimizer and checkpoint managers on the left, then pass them into the PEF-trainer configuration on the right. With the configuration set, a single command trainer.train launches the distributed fine-tuning job. Finally, we need to verify if the model actually learned the behavior. On the left, we initialize the Tunix sampler with a cache to speed up inference. On the right, we feed it a math problem using the exact same prompt template used during training. We use greedy decoding setting temperature to 0 to ensure the most deterministic and logical reasoning trace possible. The results? The model successfully adheres to the XML structure, outputting clear, step-by-step reasoning before delivering the final answer. We verified this against GSM-8K, ArcEasy, MMLU, and our custom test set, achieving consistent formatting and improved interpretability. By combining Tunix's JAX-native efficiency with a mobile-first distillation strategy, we've built a tiny giant, a 1B model that doesn't just guess, it thinks. Thank you.